So I've made progress and managed to figure out my ship's orbit. Unfortunately, my peak orbit is over 1,000,000 kilometers from the surface. I'm not sure I have enough fuel for a regular landing. Don't see any other option. I'm going to need to perform an aerobraking maneuver to reduce speed. By dipping my ship a little bit into the atmosphere, I can use the drag to shed some velocity. But if I go in too shallow, this could take weeks. If I go in too deep, well, that's it for me. But how much is the right amount? I need to add atmospheric drag into my orbital model to figure out the best aerobraking strategy. This should actually be pretty interesting, as this isn't something that Kerbal Space Program can do. The formula for drag is pretty short. 1/2 the coefficient of drag times atmospheric density times velocity squared times the cross-sectional area of the craft. Calculating each of these values can be a little more complicated. Before I get to adding this to the program, I want to clean the code up a bit first. Right now our orbit simulator takes in a couple of values, but we're going to add a lot more. To make it more manageable, I'm going to create a name tuple that we can use to pass around orbital information. Let's talk about rho first. Rho represents the density of the atmosphere. Calculating this typically depends on a variety of different factors: the altitude, the temperature, the density at sea level, the list goes on. KSP's density model is a little complicated, but KRPC has a function to calculate it. While the function isn't perfect, it should be close enough. We'll add a parameter in our init function to accept a density calculation function for a given altitude. KRPC provides this function, so we can just pass it in. A, or the cross-sectional area, is much simpler. It's just the cross-sectional area of our spacecraft exposed to the actual motion of the air. I'm going to assume our spacecraft is always pointing the opposite direction of travel, so our area is just the cylindrical area plus some of the external features. Our ship's radius is 1.25 meters, so its area is about 4.91 square meters. There's some other items attached though, so the sum of all of the cross-sectional areas of these objects comes to about 5.38 square meters. One more thing to note before we do anything else is that this function calculates the drag force. We want the deceleration due to the spacecraft. Now, Newton's second law tells us that force equals mass times acceleration, so the acceleration is just the force divided by the mass. Finally, we have C sub d, or the coefficient of drag. This is the least intuitive value to calculate and usually has to be done experimentally. The model Kerbal Space Program uses is pretty complicated and isn't actually constant, but I've run a few tests and found a good value that works: 1.455. I won't go into how I got this number, but the short story is doing several aerobraking tests and changing the number until my prediction matched my actual recorded path. Now, in our orbital calculation loop, we'll add a function to calculate the drag deceleration. All we need to pass it is our position and velocity vectors. First, we'll find the magnitude of the velocity using the norm of the vector, and plug that into the equation for drag using the other variables we've added. This is a drag force though, so we'll convert this force to acceleration using the known mass of the spacecraft. And the direction of this deceleration is just going to be opposite the direction of the velocity. So we'll normalize the velocity vector to get the unit velocity vector. Multiplying the magnitude of our deceleration with the unit vector pointing in the other direction gives us the grand total deceleration vector for drag. Now we can just add this vector to the current acceleration vector to get the sum of all of the accelerations acting on the spacecraft. I'm going to do a test burn to bring my periapsis, or the lowest point in my orbit, down. Let's run this based on the live data to see how close it is to reality. I'll fast forward just to check. My model is close enough to reality for me to be comfortable. While it's not perfect, it's good enough. Optimally, I'd like to land near the equator, which should be the warmest part. After doing some tests, I found 30 kilometers of periapsis is the best altitude. There are more scientific ways to find the best point to bring the orbit down to, but I've effectively just guessed and checked until I found something good. Next, I'll need to write a system that will fire the thrusters at just the right time for landing, so we don't accidentally use up too much fuel. In the next episode, we'll come up with a method to do just that. Stay tuned.